Let's switch it on. Let's see what it does.
Through this coil of thick wire, we're about to pass a huge alternating electric current. On top is a 1 kilogram aluminium plate.
So we hear this noise. What's that noise?
It's the vibration of the plate because it's vibrating at 2 times the frequency of this one.
Whoa! Whoa! How does it do that?
To find out, I've come to the place where it all started, the Royal Institution in London.
This is the key to Faraday's magnetic lab. It's amazing that lock still works.
From the 1870s onwards, it became a storeroom, which is why it survived, and it survived intact. All the joinery, giant electromagnet, exactly the same as Faraday
So this is exactly as Faraday would have had.
That's right, yep.
In Faraday's time, it was known that electric current creates a magnetic field, but it remained an open question whether the reverse is possible, if a magnetic field could generate electric current. Faraday answered this question with his most famous apparatus.
Faraday's electromagnetic induction ring, which is this.
In August 1831, Faraday wrapped 2 coils of insulated wire around this iron ring.
But in 1831, you could not go down to your local electrical hardware shop and ask for X hundred meters of insulated wire. You had to insulate the wire as you went, and so as you pushed and pulled the wire out of the ring, you had to insulate it. It takes 10 working days, which is a huge investment of time.
But the investment paid off. When Faraday connected a battery to one of the coils, he saw a brief pulse of current in the other coil. And when he disconnected the battery, he saw a pulse of current in the other direction. He realized that current was induced in the second coil only when the magnetic field through it was changing. And if they hadn't been wrapped on the same ring, Faraday may have noticed that the 2 coils repel each other when the current is induced, and that's due to the interaction of their magnetic fields. Which brings us back to this. Through the bottom coil, we are passing a huge electric current, 800 amps, which alternates in direction 900 times per second. This ensures there will always be a changing magnetic field above the coil. Instead of a second coil, we're using the aluminium plate, but the principle is the same. The changing magnetic field induces currents in the plate that create an opposing magnetic field, so it levitates.
How awesome is that?
This current is not only good for levitating the plate, it can also make light bulbs glow.
A gift.
Oh, thank you. Oh, that is cool.
Not too close because it will burn the arms.
Can I put it there?
Yeah.
And just as current in a toaster element heats it up, the induced current in the plate dissipates its energy as heat.
Some water too.
Thank you.
Yeah, to see the temperature.
Check out how hot this plate is. Oh, that is nuts. Is this your favorite demo?
It's like a flying barbecue or something.
Tell me this is not the best dinner table centerpiece. It levitates, it gives you light, and you can cook on it. And all the while, you're demonstrating Faraday's law of electromagnetic induction. But where do they get that matter to grow?
It's electric! Chicken and miss somebody, she's a chicken feeling jolly, she's a moving along with electric. She's so got the boogie. Don't wanna lose it. It's electric.
What is a candle flame really made of? I'm at the Palace of Discovery in Paris to do an experiment that beautifully demonstrates the answer.
Ce conducteur-là sera chargé négativement, d'accord? Par ce phénomène qu'on appelle l'influence électrique, celui-ci sera chargé plus.
Okay, so we're turning on an electric field here. You can see that the flame is spreading
Yeah.
out. Quel est le voltage ici?
Il doit être à peu près 20 000.
20 000.
On voit bien tes papillons ou non? Oui.
Papillon?
Papillon, ça fait comme
Oui,
ça.
oui, oui.
Comme un papillon.
Oui. That's very cute. It's like a butterfly.
Alors la flamme, c'est un plasma. C'est un milieu totalement ionisé.
And you can see that the flame has two separate pieces to it now. One is going towards the negative plate, and those would be the positive ions, and the negative ions will be going towards a positively charged plate. So we see the flame kind of flattening out.
But if that didn't convince you that a flame contains ions, then check out part 2 of our experiment where we compare the conductivity of a flame to the conductivity of air, which is normally a pretty good insulator.
It requires about 10,000 volts to break down a centimeter of air. So right now, this plate is at about 10,000 volts. You see that the spark is only a little. But if I put it around the flame, we'll see if we can get a bigger spark to happen. Look at that. Yeah. Because the flame has those ions in it, it means that we can break down a greater distance of air because there's greater conductivity. Yeah. That's awesome. You love doing this, right? Yeah.
A strong enough electric field can actually extinguish the flame, but watch carefully what happens when the flame goes out.
Regarde,
Wait.
on voit très bien.
Il y a des ions dans la fume.
Oui, tout à fait.
Just like in the flame, the opposite charges in the smoke are pulled in opposite directions. Now, while some may argue that a flame is not truly a plasma because it's not hot enough and it doesn't have a high enough density of ions, one thing is for sure, it does contain ions which have important electrical properties which can be demonstrated if you have a strong enough electric field.
Regarde. Ah!
It's electric. Woogie, woogie, woogie. Better know it's there. Heaven and everywhere. Teach you, I'll teach you the electric slide. Woogie, woogie, woogie. You can't see it, it's electric. Woogie, woogie, woogie. You gotta feel it, it's electric. Woogie, woogie, woogie. Ooh, it's shocking. It's electric. Woogie, woogie, woogie. You gotta miss a Kelly with the problem that she's a moving along with electric. She's all got the boogie. You gotta